Good afternoon, everyone. My name's Jo. I'm a lecturer in astronomy at the Open University in the UK. And today I'm going to talk to you about why and how we look at the atmospheres of extrasolar planets. An exoplanet is a planet that orbits a star other than the Sun. And until about 25 years ago, we didn't even know that any of these existed. But now we know that there are thousands and thousands, so we want to find out more about them to see what makes them tick. I'm just going to share my screen for you now. And hopefully that will work and you can see my presentation. So I do something that can be thought of as being an exoplanet detective. I spend my research time trying to find out what's going on with all of these planets that orbit other stars. And the reason that I do that is to really get a handle on some of the big questions that occupy humanity and have done for a very long time. Because understanding what's going on with other planets in other planetary systems can tell us more about how we got here, how our planet got here. It might be the key to finding out whether there's life elsewhere in the universe. And it also helps us to understand how planets work. And that's actually a pretty important thing. At the moment, of course, we're running a rather big and rather ill-advised experiment called What Happens If We Pollute Our Atmosphere with Tons of Carbon Dioxide? So rather than continuing with that experiment, it's better to look at what happens to other planets that might have different conditions and see what happens there rather than trying to see what happens if we wreck our own. Until the first exoplanet was discovered, this was all that we knew about planetary systems. We knew that there were 4 small rocky planets in our system that were relatively close to the Sun. We call those as terrestrial planets, which just basically means they're fairly similar to the Earth. And then further out from the Sun, we have 4 large gaseous planets. And that was all we knew. Now, we could infer certain other things from looking at this system, one of which is that only a subset of those planets have the right conditions for water to be a liquid on the surface. Now, life as we know it seems to require liquid water to exist. So if we want to find life anywhere else in the solar system or outside it, then we need to look for those appropriate conditions. And by far the biggest variable there is temperature. So as you go further out from the star within a planetary system, the planets are going to gradually get cooler because they're receiving less radiation from the star. So in our solar system, Earth has about the right amount of radiation from the Sun to have an appropriate temperature for water to be a liquid as opposed to a gas or ice. Mars is a little bit too cold, on the other hand. So whilst we think that Mars did have liquid water at one point in its past, we see a geological evidence for that in the form of structures that look like they were at one point river valleys that were carved out by water. Now it no longer has liquid water, although it does have water ice at the poles. Venus is too hot. It's quite close to the inner edge of the habitable zone. Just based on its distance from the Sun, we might think, well, maybe Venus is on the edge. Maybe Venus could just about have some liquid water. Well, as it turns out, Venus is a little bit like Earth's twin in the solar system. It's a very similar size, similar mass, and receives a similar amount of radiation from the Sun. So what is Venus like? There have been lots of hypotheses about what it might be like on the surface of Venus over the years before the space age got going and we were able to send robotic spacecraft to actually have a good look. So initially, sort of around the turn of the century, the 20th century, people thought maybe Venus was actually an ocean world. Maybe there was lots of liquid water there and it was just a little bit tropical, a little bit warmer, actually quite a pleasant place to be. That was revised somewhat later when people argued that no, it's not an ocean world, maybe instead it's a desert world. So still, broadly speaking, not too dissimilar to what we have on Earth, but probably a little bit warm for there to be lots of liquid water. Now, what we now know, thanks to spacecraft that have visited Venus and actually taken direct measurements, is that Venus is nothing like the Earth at all, despite the fact that it receives not very much more radiation from the sun than the Earth does. It's a 450 degrees C hellscape with acidic clouds and enormous atmospheric pressure. It's nothing like the Earth. So, given that they probably started out not too different, what went so horrendously wrong for Venus? Well, it's our good old friend, the greenhouse effect, that comes into play here. So what we think went wrong for Venus was it probably did start off with a liquid water ocean. We've got evidence that there used to be a lot more water in Venus's atmosphere than there currently is. So if you start with a liquid water ocean, that's pretty useful because it's good at absorbing carbon dioxide from the atmosphere. In fact, our own ocean has acted as really quite a good buffer against the effects of climate change and us putting more CO2 into the atmosphere by reabsorbing some of it all the time. So Venus probably started off something like this, but then because it was closer to the sun than Earth and did have that little bit of extra radiation, it got just a tiny little bit too hot. So the ocean started to evaporate and the water ended up as a gas in the atmosphere. Now, gaseous water is actually an extremely efficient greenhouse gas. That's because it absorbs a lot of infrared radiation. So once you put water vapor into the atmosphere, the planet's going to heat up a little bit more. And it's going to carry on evaporating the ocean, so there's going to be more water in the atmosphere, so it's going to get even hotter, and we have a positive feedback loop that results in eventually the entire ocean evaporating. Then what happens? You've got a lot of water vapor in your atmosphere that's now got pretty hot, and water vapor doesn't like it when it gets too hot. In fact, it starts to dissociate. So there's now no more water ocean that's stopping the carbon dioxide from getting into the atmosphere. So the water molecules get hot, they break apart, and they escape as hydrogen and oxygen atoms away from the top of the atmosphere. And so instead of water in your atmosphere, you now have all of that carbon dioxide that might have been trapped in the ocean that's released into the atmosphere. So you have 450 degrees of greenhouse warming because you have an atmosphere that's made of nearly 100 times much as Earth's entire atmosphere, but just carbon dioxide. So we can see in our own solar system how quite small differences can dramatically change how planets evolve. But to learn more about how that works in other planetary systems, then we have to start looking at the exoplanet population. That's actually quite a challenging thing to do. I'm sure you've all stood outside and looked up at the sky at night, and you can see lots and lots and lots of stars. But apart from a few of the planets in our own solar system, you won't have seen a planet in the night sky. And that's because planets are relatively small and cool and faint compared with their parent stars. So to actually see one of those planets, it would be like looking at a glowworm next to a lighthouse. It's just not something you can do, even with an extraordinarily powerful telescope. So the methods that have been developed to find exoplanets are indirect methods, and they both rely on measuring the effect of the exoplanet's presence on what the star is doing. So the method that has been the most successful, that has discovered the vast majority of the exoplanets that we now know exist, is called the transit method. And this relies on a little bit of luck, because for this to work, the planet and the star have to be lined up just right, so that at some point during the planet's orbit, it blocks some of the starlight. If we have a telescope that's staring at that star for a period of time, and we measure a dip in the amount of light coming from the star, then we can infer the presence of a planet around that star. The amount of light that's blocked, so the size of that dip, tells us the relative size of the planet against that of the star. So a smaller planet will block out less light from the star, and so we'll see a smaller dip. So from this method, we can obtain actually a measurement, not only of the fact that the planet is there, but also of its physical size relative to the size of the star. Fortunately, we're quite good at determining the size of a star, so that means we actually know what the size of the planet is. And various space-based and ground-based telescopes have detected planets in this way. So on the ground, we have the Super WASP Observatory that's still going, and that has discovered a vast number of planets that we call hot Jupiters. So that's good at discovering planets that are about the size of Jupiter. Until fairly recently, the Kepler spacecraft was operational, and that stared at a particular patch of sky in the constellation of Cygnus for several years, measuring the brightness of all of the stars in that field of view continuously. And Kepler on its own has discovered thousands of exoplanets, including planets that are probably the same size as Earth. And more recently, the TESS spacecraft has launched, and this is particularly exciting for me. I'll talk more about why later, because this planet is surveying all of the brightest stars in the sky. So it's looking for all the planets around our neighbouring stars. So that's one method that we can use to indirectly detect an exoplanet. The other method, and this is the method for which two astronomers called Didier Queloz and Michel Mayor were awarded the Nobel Prize last year, is what we call the radial velocity method. And it relies on the fact that something that you were told probably in your physics or maths lesson at school is actually a lie. So most of the time, when you're doing a physics or maths problem at school, and you're doing something to do with orbits, so you have either a spacecraft orbiting the Earth or a planet like the Earth orbiting the Sun, you're told to assume that the smaller thing in that equation doesn't have any mass. It's what you call a test mass. You're pretending it's massless. And that makes the maths behave much more nicely, because you can assume that the big thing, the thing in the middle, stays completely still and doesn't move. Now, of course, this isn't true. Planets have mass too. They have much less mass than stars, but they still have some. So what this means in practice is that when a planet orbits a star, the star doesn't stay perfectly still. What actually happens is the planet and star together orbit a point in space called the common center of mass. Because the star is so much more massive, that point in space is usually still within the star, but it means that the star wobbles around a little bit as the planet orbits. And that depends on how massive the planet is. So the more massive the planet is, and also the closer to the star the planet is, the bigger that wobble is going to be, and the faster the star will move. So if we can see that a star is wobbling in a particular way, we can infer the presence of a planet in orbit, and we can calculate its mass. But how do we actually see that the star is wobbling? If it's making such small movements that the point at the center of the system is still actually within the star itself, then how on earth can we see it? Well, that relies on something called the Doppler effect. So if an object is emitting light and it moves towards you, light is a wave. So that means that as the light's emitted, because the object's coming towards you, that wave of light is going to get a little bit squashed. And what that means is that the light is going to apparently change colour and become a little bit bluer. On the other hand, if the object emitting light is moving away from you, then the light is going to get stretched out, and that makes it look a little bit redder. Because there are chemicals in the outer parts of the star that absorb particular colours of light, and we know what those are very, very precisely, then we can detect even very, very small changes in the colour of the light coming from the star. So we can detect these stretches and compressions of the light wave. So this has been done for a number of stars, and it's been confirmed that they do indeed have a planet in orbit around them, because we can detect that the light from the star is stretching and compressing as the star moves towards us and then moves away from us again. So to do this, we need different kinds of instruments. What we need are very, very precise, very stable instruments that can split light up into lots of different colours and do it at very, very, very fine resolution. So This is best done from the ground because we have more control over the stability on the ground. So at the Very Large Telescope, which is actually multiple telescopes that can operate either individually or together, we have an instrument called ESPRESSO, and that works with all of the 4 telescopes operating together. And there's also an observatory called Lucilla, which there is a telescope called, an instrument, sorry, called HARPS. And these 2 instruments have discovered lots and lots of exoplanets using the radial velocity method. So if you have both a transit measurement and a radial velocity measurement for your planet, then you've actually got quite a lot of information, because you know the mass of the planet based on the wobbling star, and you know the radius or the size of the planet based on how much light it blocks during its transit. That means you can calculate the density of your planet, because density is just equal to mass over volume. You also know the distance between the planet and the star, because for both of those methods, you also get for free the period of the planet's orbit, how long it takes for it to complete a single orbit. And the period is related to the distance between the planet and the star. And we can use that to estimate the planet's temperature, because the temperature is proportional to the square root of 1 over the distance. And that's related simply to how the light from the star gets spread out over a wider and wider area the further away you go from the star. So that means that for some planets, we already have a very good idea of what they're like before we do any further investigation. And these planets are the hot Jupiters. So anything that's about the size of Jupiter, typical radius of 1 Jupiter radius, is going to have a fairly similar mass to Jupiter, but actually many of them have slightly lower masses than Jupiter does. So that means they're lower density. And unlike the planets in our own solar system, which at maximum have temperatures of a few hundred degrees, the typical temperatures of these planets are about 1500 degrees. And that's because they orbit their stars with periods of only a few days. So they're extraordinarily close to their stars. Typically, they have distances between them and their stars of about a few % of the distance between the Earth and the Sun. Because we know their density, we can confidently say that these are all planets dominated by hydrogen and helium. So they're made of the same stuff as the gas giants in our own solar system. So knowing the density and the temperature does help, and it's allowed us to confidently say that all of those hot Jupiters, they're gas giants. They're like the gas giants in our own solar system, but they've just been heated up quite a lot. However, if you look at smaller planets, then we start to have quite a bit of ambiguity. So in our own solar system, the largest rocky planet is the Earth, and the smallest gas giant planet is Neptune. Neptune is 4 times the size of the Earth, so the radius is 4 times bigger. That's actually quite a big difference, and it turns out from looking at the planets we've discovered elsewhere orbiting other stars that there are lots of planets that occupy this gap in between the Earth and Neptune. And that's where we get a little bit more confused, because we don't really know at the precision to which we can currently measure their radii and their masses whether these are more likely to be large rocky things or small gas things. So in this diagram, which is a little bit complicated, on the y-axis you've got the planetary radius in terms of Earth radii, and then in a log scale on the x-axis you have the mass in terms of Earth masses. And these lines are lines of constant composition. So if something has a composition of 100% iron, then if you plot its mass and radius, it would fall somewhere along this line. If it's rock, then it would fall along the orange line. If it's 50% water, this pale blue line, and so on. But you can see that because the error bars on these measurements are quite big, a lot of these planets span multiple lines. So we still don't really know what they're like. And that means we need more evidence. We need to find out more about these planets. We can't just zoom in and take a picture. So we need to find a way of getting that evidence using those indirect methods that we talked about for planet detection. And the thing that we can use is a technique called spectroscopy. So when I was talking about the radial velocity measurements and the wobbling stars, I mentioned that stars have gases in their outer layers that absorb particular colours of light. And actually, the presence of those absorption lines is how we know what chemicals are present in the outer layers of stars. So this is a sketch of where those lines fall in the visible spectrum for our sun. And these darkest lines in the sun's spectrum are called the Fraunhofer lines. So these each correspond to different chemical species. So this double line here, for example, is absorption from sodium gas. This is the same sodium gas that gives old-fashioned sodium street lights that orangey yellow colour. So it's the same feature here that's absorbing in the outer layers of the sun. We've also got things like iron and oxygen and calcium. So this works because light from the sun is emitted from a region that we call the photosphere, which literally means the sphere that emits photons. And the light passes through cooler gas on the outside of the sun before it makes it into space. Some of those wavelengths or colours are absorbed before they can escape to space. So in this particular case, the absorbing gas is sodium. You can see that the colours on either side of sodium make it all the way out of the sun, but the colours right in the middle don't. Now, let's go back to our planet that transits in front of its star. So when an exoplanet passes in front of its star, then actually the same thing can happen, but with the exoplanet's atmosphere. So if you imagine that your planet's sitting in front of the star, the solid bit of the planet, the totally opaque bit, that's going to block light of all colours. And that's the bit that's producing the bulk of that dip in the amount of light we see from the star. But some of the starlight is going to pass through the atmosphere of the planet, the shell of gas that surrounds the outer region of the planet. And if that planet has, for example, sodium gas in its atmosphere, then light that has the colour that is absorbed by sodium gas isn't going to make it through the planet's atmosphere, whereas other colours will. What that means in practice is that the transit of the planet will actually look deeper in the wavelength where the planet's atmosphere has an absorbing gas. So the planet looks bigger here in the centre of that sodium absorption band compared with the colours either side, because the atmosphere is blocking the starlight as well. Now, we can do this not just for visible wavelengths, but actually for lots of different wavelengths. And we can do this using telescopes such as the Hubble Space Telescope and the Very Large Telescope on the ground. What's really exciting is that hopefully next year, coronavirus permitting, the James Webb Space Telescope is going to launch. This is a telescope that has a 25 square metre primary mirror. You can see that mirror in all of its glory in the picture. And because it has such a large mirror, that means it can collect lots and lots of light, and it can give us really, really precise measurements. So everybody's very excited about what James Webb can do. The other thing that's important about the James Webb telescope is that it observes in the infrared rather than in the visible, which is actually the bit of the electromagnetic spectrum we're most interested in if what we want to know about is what gases are present in exoplanet atmospheres. So this is showing a visible light spectrum for an exoplanet called WASP-96b. It's a hot Jupiter. This was taken from the Very Large Telescope. And what you can see here, this is what's being measured here, is the size of that dip during the transit, what we call the transit depth. So you can see that in the middle of this sodium band, the planet appears to be bigger than it does on either side of that band. The reason it's not just a single spike is because absorption features get broadened out if you have high pressures. So because the gas in the atmosphere, certainly at the deep regions of the atmosphere, is under quite high pressure, you see that it gets broadened and it gives you this very characteristic shape. So we've detected sodium, and actually we've got lithium in here as well in an exoplanet atmosphere. But of course, in reality, it's more complicated than that. Often we can't just take a quick look and say, yes, this is definitely sodium or potassium or water vapor. Certainly, when we go further into the infrared and we're looking at molecules, so things like water vapor and carbon dioxide, rather than atoms like sodium, the features tend to overlap with each other. So what we need to do is perform a sort of EFIT. we need to make lots of different models of exoplanet atmospheres and simulate light shining through them and calculate what we'd see on the other side. And then we can compare those with the actual observations. So in this really contrived example, you can see that the green model is the only one that produces something that actually looks like our observation. So this is another example of a hot Jupiter spectrum. This is actually an ultra hot Jupiter, has a temperature of well over 2000 degrees C. And this is a spectrum taken from the Hubble Space Telescope, both in the visible over here and in the infrared part of the spectrum just here. So it looks a lot messier than the last spectrum I showed you. And we think we've got lots of different things going on here. So this wiggly bit over here, when you've got lots of things going up and down, that characteristic sort of comb of features, we think is probably vanadium oxide, which has that particular signature. Then over in the infrared here, we've got two bumps. This one we think is iron hydride. And then here we think we've got, surprisingly enough, water vapor. It turns out that even at these temperatures, you can still have water vapor present as a gas in an atmosphere, just not very much of it. So it's what we call a trace species. And then we think this weird slope over here might be something called SH, which is a radical species made from sulfur and hydrogen. That is a little bit speculative. So now you can see how we can put this sort of information together. I'd like to talk now about one of my favorite planets, which is actually a planet that's really messed with our ideas of how planets should behave and made it very difficult actually to work out what's going on. So this is called GJ1214b. If you haven't worked it out already, we're really rubbish at naming planets. So GJ1214b was everybody's dream when it was discovered, because it's one of those planets that falls into the size gap between Earth and Neptune. So it's one of the ones that we really desperately want to learn more about. It was detected transiting. That's good, we can get the radius. And the star it was transiting was a nearby cool star. That's great, because that means it's quite a small star, but because it's nearby, it's bright. So that means we're going to get a nice, big and clean transit measurement. It was an ideal prospect for doing this kind of transit spectroscopy. So everybody went a little bit mad. And everyone thought, let's use everything, all the telescopes, all the instruments, whatever we can get. So that collective effort produced a spectrum that looked something like this. Now, the first thing you might think is it looks a bit messy, and it does. Either there's something weirdly zigzaggy going on over here, or it's just noise. And also, within the error bars on those measurements, it looks kind of flat. And that was the first thing that was apparent to everybody. It looked kind of flat. We weren't seeing so many lumps and bumps as we saw for those hot Jupiters. But what we did think we saw was water. So this little bump that's outlined by those green points, it looks like water. So everyone thought, okay, well, it's flat, but it looks like we've got water. Maybe that means we've got a water world on our hands for the first time. Because that feature is much smaller than we would expect if we had an atmosphere like a miniature Neptune with lots of hydrogen and helium. So water atmospheres are going to be heavier than hydrogen and helium atmospheres. And that means they kind of get vertically squished. They're a bit thinner. So this is what we might expect if we had a hydrogen-helium dominated atmosphere for this planet. But if instead we make it 100% water, it goes much flatter and looks something like this blue line here. So that was great. Everybody decided it's the first water world and it's going to be fantastic. However, there was one thing that hadn't been considered that could also produce a really, really flat spectrum. So this second hypothesis was proved to be correct when another team went back and re-observed this bit of the spectrum here with the Hubble Space Telescope, but this time they did it 15 times. So that meant that they could average all the measurements together and get a much more precise measurement. So the new measurement looks something like this black line. Now that is about as flat a line as you will ever see in spectroscopy. So we don't actually detect any features in this spectrum at all. It can't be that this is just a bare lump of rock without an atmosphere, because it's too low density for that. We know it has to have some atmospheric component. So what's going on? Well, the answer is clouds. So just like clouds ruin your ability to see anything in the sky when they're overhead, they stop the sun's light from getting through and warming us up. When they come right down to the surface and you have fog, you can't see anything. Clouds are also problematic for people trying to do transit spectroscopy. The reason for that is that they're really good at blocking light over a broad range of wavelengths and colours. So if you stick clouds in your atmosphere, then you stop all of the light, all of the wavelengths, all of the colours from getting through. So what you effectively create is a sort of artificial surface in your atmosphere, and that means you can't see anything anymore. So have things moved on at all? Well, up until very recently, GJ1214b was probably one of the smallest planets for which we had a reasonable amount of spectroscopic observations. And annoyingly, it was cloudy and we couldn't see anything else about it. But towards the end of last year, a controversial exoplanet came along called K218b. K218b was observed during the second phase of Kepler's mission. So it's got fairly similar vital statistics to GJ12 in that it's about two and a bit times the radius of the Earth. It is slightly more massive, but still probably too low density to be just a lump of rock. And two teams using the same data both found that there were signatures of water vapor in the atmosphere of this planet. And what's more, this planet is in what we think of as the liquid water habitable zone of its star. So the temperature that we estimate for this planet would allow liquid water to exist. So this made K218b the smallest known exoplanet with atmospheric water. So all of the models with water produced a good fit. It's got a quite thick atmosphere with a density of about 3/5 that of Earth. So it's probably it could be a bit of rock with a puffy atmosphere, or it could be a gas giant thing, but with heavier stuff than hydrogen and helium in. Now, as you might expect, this was exciting, and the whole community thought this was really exciting. But there were two key things that got mentioned as part of the press discussion here, which was that, number one, we've detected water. And number two, it's in the habitable zone. Now, all that really means is that if there's a surface, then liquid water could exist. But as you can imagine, the press coverage took it a little bit farther. So rather than just saying the planet was in the habitable zone, it became a potentially habitable planet, thanks to BBC News. It was found on a potentially life-friendly planet. Best candidate for habitability that we know right now? Not so sure about that. It was found on a habitable super-Earth, really not habitable zone, not the same thing. Giant super-Earth could support life, maybe. Could be key to scientists finding alien life. Yeah, so now what I would like to do, when I've posted this out, I'll put a vote up on Twitter so I can see what everybody thought. You get to decide whether we think K218b is really habitable. So I'll present you briefly with some evidence, and then once this goes live, I'll get you to make your decision via whatever platform you're viewing it on. So, evidence that K218b is actually not habitable. It's likely to have a thick atmosphere, and that probably means it has some hydrogen and helium in it. So it's probably not really an Earth-like atmosphere. So that means that the conditions on the surface, if it has a rocky surface, they're going to be quite different to conditions on Earth. Also, water being detected in the atmosphere, it doesn't mean that there's actually any water on the surface. And we don't really know if this is a rocky body or if it's something that's a little bit more like a miniature Neptune, because the density makes it a bit ambiguous. Evidence that it might have water or might be habitable. Well, it is in the habitable zone. So it does have the right temperature for there to be liquid water. It's not that much bigger than the Earth, so it's likely to be at least partially rocky. And if you've got water in the atmosphere, then it's not a big stretch to assume there might also be some water on the surface. So I'll leave everybody to have a think about that and tell me what they think is correct. Is K218b habitable, or did the press get a little overexcited perhaps? Who knows? Yes, and I should say the status of K218b will be unaffected and any extant life will remain blissfully unaware of your decision. So after K218b, what does the future hold? Well, K218b was particularly impressive because it means that for the first time, we're getting to the point where we can detect absorption from molecules in the atmosphere of planets that are really quite small. And that means we're getting closer and closer to actually detecting something in the atmosphere of an Earth-sized planet. One of the things that we'll be looking for in the atmospheres of planets that are Earth-sized and potentially in the liquid water habitable zone is ozone. And that's because ozone is an indirect biosignature. The reason that we have so much oxygen in our own atmosphere is because life is continually resupplying it. And when that oxygen interacts with photons high up in the Earth's atmosphere, ozone is formed. Now, we could detect the presence of an ozone layer, if it's there, with the James Webb Space Telescope. So these are some simulations that I performed. So the black lines are a simulation of what a spectrum of an Earth-like planet might look like with the James Webb Space Telescope. This little bump over here, that's ozone. And only models that contain ozone would produce a good fit to that synthetic spectrum. So we could detect it. And not only that, we actually have a candidate system within which this would be possible with James Webb in the next few years. And that's the TRAPPIST-1 system. So this is a system of 7 rocky planets around a very, very cool, very, very small, but close by red dwarf star. So because the star is small and cool, the habitable zone is actually really, really close to the star itself. So that means that some of those planets, probably the middle 2 or 3, are in the liquid water habitable zone for this star. That means they could potentially have Earth-like atmospheres, although that's highly dependent on whether Earth-like atmospheres could form around a star like that, which is something that we don't really know yet. After James Webb, we will also see the launch of the ARIEL spacecraft in about 10 years' time. So this is a mission that I'm very proud to be involved in, and it's going to look at the compositions of 1,000 exoplanet atmospheres. James Webb, as fantastic as it is a multi-purpose observatory, so we're not going to be able to study all of the interesting planets that we would like to. But with ARIEL, we can do a much larger number. And for the first time, we'll really be able to get an idea of how planetary atmospheres work in general, rather than for a specific few cases. So thank you very much for listening to my talk. I hope you enjoyed it. Please do get in touch with me online if you have any questions. I'd love to hear from you and continue the discussion. And finally, I hope that you're all staying safe and well during the current very difficult circumstances. Thanks a lot. Bye for now.